Hey guys, this is Coach Brian coming to you with the 9.2 notes. This is all about arc and chord relationships, a lot of relationships between these two things. So just want to make sure that we cover all of them. I'm going to try to move pretty quickly here. And remember, you can always rewind it, slow it down, go back, whatever you need to do if you're not sure about these. All right, so let's go ahead and jump right in. Our first definition here says that the measure of an arc is the measure of its central angle. So see right here, I have a central angle. An angle that's vertex is in the center of the circle. So I have this central angle, and using that number or that angle, all right, we can measure, or we have the measure of the arc, okay? So that is measured by taking the angle. In this case, we could name it BAC. All right, the A just has to be in the middle because it's the vertex. And we could say that it is equal to the measure of arc BC, okay? Angle BAC equals arc BC. And then next, if we have adjacent arcs, so neighboring arcs, see how we have A to B here, and then we have B to C, all right, and they're right next to each other, they're adjacent. Their measure can be found just by adding together their two arcs. Think about it. If they're both coming from a central angle like this, and based on what we just said the arc is the measure of the angle, we could just add them together, and that will give us our arc. On this first example, it says to find the following arcs. So it asks us to find the measure of CF. So the first thing we need to do is find C, and then we need to find F. And one thing I want to point out is that this arc is named with only two letters, and that means it's a minor arc. So if you're not sure like which way to go, should you go this way or this way? Well, 2 letters are a minor arc, 3 letters will be a major arc. And if you're not sure about what those mean, you need to look back at your definitions. A minor arc is going to be anything less than 180 degrees, so less than a half circle. And a major arc is going to be anything greater than or equal to 180 degrees. So you see how going this way would be over half the circle? That's a major arc. We're only dealing with the minor, so we're going to go from C to F the short way, okay? So to find the arcs, you can see we've got 2 adjacent arcs here, BC and BF, that are adjacent. So what we would do is we would add them together. 52 degrees plus 60 degrees gives me 112 degrees arc. The next one I want to find is the measure of E to D. E to D. And so going from E, again, just 2 letters, and taking this short way, D right here. All right, at first, it looks like we might not have enough information to do this, but if we use, or if we observe that our circle has a diameter, you can see right here from E to B, that's our diameter. We know that a half circle, all right, this entire arc right here, entire arc that I just put in purple, so we could call that arc, we call it ECB, is 180 degrees. And then we can see that it's made up of a 52 degree angle and a 90 degree angle, and then the angle we don't know that we'll just call theta. So those 3 numbers need to add up to 180. So we have 180 minus 90, that gives us 90, minus 52. And that leaves us with 38 degrees. And that is what arc ED must be so that it can complete the half circle or the semicircle. All right. 2 minor arcs. Minor arcs, again, just arcs going from less than 180 degrees of the exterior or perimeter of the circle. They are congruent if and only if their chords are congruent. So see here we have chords AB and chords CD, and they have this little mark on them showing that they are congruent. Since they're congruent, think about it. If I went from this end to the center, this end to the center, this end to the center, and this end to the center, those lines are congruent. So their central angles are also congruent, which means their arcs are also congruent. In our second example, it says to find x. So we are looking for x right here. And now our only clue is that these arcs are congruent. And so since this has if and only if, that means it's biconditional, which means it's also true when it's read the opposite way. So we can say if two arcs are congruent, then their chords are also congruent. So if these two chords are also congruent, we can just set them equal to each other. We can say 9x minus 34 equals 4x plus 1. So what we'd do is we'd add 34 to both sides, and then we'd subtract 4x, and we'd end up with 5x equals 35, and x equals 7. All right, just a couple other notes right here real quick. The perpendicular bisector, remember that means two things. It means 90 degrees and it means cut in half. So if a chord, all right, we have a chord, in this case it would be IN, the green line that I'm tracing right now. If we find its perpendicular bisector, so that means it's got to do two things. It cuts it at 90 degrees and it cuts it in half. See the little marks that mean that's equal to that? If we find a chord's perpendicular bisector, that same perpendicular bisector is the diameter. See how it goes straight through the middle of the circle from side to side? So right here, you can barely see it, but there's a T right there, okay? A little T. So if from I to T is congruent to T to N, and, all right, got to be both things here. That's the bisector part. And if IN is perpendicular to KR, all right, don't forget this is the sign for perpendicular. Okay, if those two things are true, then KR is a diameter. All right, and then we can also, use the opposite of that. We can say that if the diameter of a circle is perpendicular to a chord, then it bisects the chord and its arc. So kind of building on what we just said, now we're saying if you have a diameter, like in this case, KR, if it is perpendicular to a chord, then it not only cuts that chord in half, so we could say that this side, let me get a different color, this side equals this side, it also bisects the arc. So we could say that arc IR is congruent to arc RN. All right. Moving ahead, we have some examples based on the things that we just talked about. First one says find X and find Y. All right, so we have some information here. You can see we have a chord. We have a line going through the center of the circle from one edge of the circle to the other. And we know that they cross at 90 degrees. So starting with the red one that goes through the center and goes from side to side, that's a diameter. Okay, so we have a diameter in red, and it intersects a chord, at 90 degrees. So that means it is perpendicular to the chord. And if we go up here, it says if the diameter of a circle is perpendicular to a chord, then it bisects the chord and its arc. So what that's telling me is that this chord segment and this chord segment are congruent, and also this arc and this arc are also congruent because this red line is bisecting them both. So that means I can take my two arcs and I can set them equal to each other. And I can also take my chord segments and set them equal to each other. And so just really quickly doing some algebra here, I'm gonna add 18, subtract 3x, divide both sides by 2, x equals 7, and now I gotta find y. So I am going to subtract y and subtract 1. And I get that 3 equals y. So there's my x, there's my y, 3 and 7. All right, example number 4 says to find x. So I'm really looking for the hypotenuse of this like mini triangle within my circle. And now I see a couple things. I see that this line, even though I only know that part of it is 9, I know that it starts in the center and that it crosses this chord at a 90-degree angle. So what that's telling me is that it is bisecting the chord. So it's taking this 32 and it's splitting it into 2 equal parts. So now what I've got is a right triangle that I don't know the hypotenuse of, but I do know the 2 sides of, so I can use the Pythagorean theorem. And in this case, x is my c, it's my hypotenuse. And so I'm gonna set it up using my sides. And so 9 squared is 81. 16 squared is, I believe, 252, but let me confirm before I put a wrong number on here. I can't type on my calculator. 256. Glad I double checked. And so when you combine those together, that gives you 337. All right, and that's still c squared. So what I got to do is find the square root of both sides. And the square root of 337 means that my hypotenuse is about 18.36. All right, last couple bits of our notes. 2 chords are congruent if and only if they are equidistant from the center. So now we've got a new way of determining if chords are congruent. If we can prove that a line connecting them to the center of the circle makes them equidistant from the center. So what we would say here is if the distance A to O is congruent to O to B, then the 2 chords, which are F, G, and HJ, we would say that they're congruent if we can prove that they're both equidistant from the center. And so over here, using our example, number 5, we can see, hey, these are at right angles to each other. Okay, that means they're both coming from the center at the same approach to the chord. And then they are also congruent. That's what the little mark means. So what we've just proven is that these two chords are the same distance from the center. And if they're the same distance from the center, they are congruent. And so I can set them equal to each other. And once they're equal to each other, I can use algebra to solve for x. And x equals 7. X is equal to 7 a lot today. All right. The products, so that's multiplication. All right. The products of the lengths of the line segments on each chord are equal, okay? The products of the lengths of the line segments on each chord are equal. So what this is saying is that A times B, okay, the two segments, A and B, see how they're on one chord, are equal to DC. And so what this does is it kind of allows us to find some missing or unknown chord lengths when we only know, certain pieces of information. And so I think the best place to show this as an example is, or the best place to see it in action is to use an example. So you can see here we've got a chord that I'm kind of outlining in this dark color, and then I'm going to outline the other in blue, just so you can see what kind of works together. And so what I've got is, the 3 and the 4 go together, the 7x and the x go together. And so what I'm saying is that I can take these segments and multiply them by each other, and they should be equal, okay? So on the left side, 3 times 4 is 12. But on the right side, I've got a binomial and I've also got a variable. So I've got to distribute this. Okay, I've got to distribute this. So x times 7 is 7x, and x times x is x squared. All right, so at first thought, you might be thinking, okay, I got to move some things over. I got to divide. I got to this. But what we should do in this case is we should try to move everything to one side and get this equal to 0. So what I'm going to do, since I know that this x squared is going to be my first thing in my trinomial, I'm going to actually add it to the left side. And I'm going to subtract 7x. And then I've still got my positive 12 over here. And what you've noticed is I've left nothing on this side. I got rid of all of it. And then, to figure out our solutions, we would need to factor. I know you thought we got rid of factoring, but you never get rid of factoring. It's always here. It's never going anywhere. And so, just real quickly, we would use, I'm sure your teachers taught you a lot of different methods, but we would use AC, or I use the AC method. And so what that means is I take A, which is 1, multiply it by C, which is positive 12, and then I take my B value, negative 7, and I need to find magic numbers. I need to find numbers that multiply to equal 12 and add to equal negative 7. And so I've got some clues here. First thing is that my product is positive, but my addition is negative. See that? So that means both my numbers are actually going to be negative. And 2 negatives multiplied to give me a positive, and then they're going to add together to give me a more negative number. So I've got negative 3, negative 4, and when I add those together, I get -7. So those are my magic numbers, and you might have in Algebra 2 used box method, but once you can split your binomial, you would just write that out and then put those into the box where you would further factor them. So hopefully this is ringing some bells for you from algebra, but we'd factor to the left. And so on this side, I can take out, let me actually write this a little bit bigger. But on the left side, or excuse me, the top row going to the left, I can take out an x from both of them. And then on the bottom row, I can take out a -3. And then after you factor to the left, you factor vertically, okay? So what can I take from both of these? I can take an x. What can I take from both of these? I can take a -4. And if you're unsure about this, you can just confirm. Is x times x x squared? Yes. Is -4 times x -4x? Yes. Is -3 times x -3x? Yes. Is -3 times -4 +12? Yes. So my answers up here, I know this is a long problem. My answers up here are that x -3 and x -4 are my intercepts, and I would just set those to equal 0, and I would get that x equals 3 and 4. That was a throwback to Algebra 2 right there. All right. Last one, I'm going to let you solve on your own. Hopefully this helped. Make sure you do your practice also, and ask me or your teacher if you have any questions or need any more help. Thank you.